We have talked about inertia previously, and inertia is the resistance of any given object to change motion. And this resistance, well, when we ever talk about linear motion, in linear motion this resistance is given by mass. So we usually state that mass is the inertial property. The more the mass, the more difficult it is to change the motion of something. But whenever we talk about rotational motion, well, mass is important, yes. It is important, the mass, but it is also important how mass is distributed. So mass and the distribution of mass are both important concepts in order to generate the rotational inertia. The rotational inertia, best known as the moment of inertia, will state that it's given by the letter I, and it's going to be given as an integral of r squared dm. If we have just particles, well, it's just the sum of where the mass is located at a certain space. So the more the mass, the more the inertia, the more the radius, which is the distance, for instance, from the rotational point to any given point here, for instance, the more it is, well, the more the moment of inertia. And this is an integral. And we're not going to integrate. We have moments of inertia already reported. But the units of this guy are, for instance, kilogram. So kilogram times meter squared. Are the units of the moment of inertia. So it is important to understand if the mass increases, the moment of inertia increases, but it's also important to understand that if there are particles that are farther away from the moment, from the axis of rotation, then the moment of inertia increases as well. And there are already reported some moments of inertia. For instance, a slender rod axis through a center, that's the first one, 1/12 of the mass of the whole rod times the length of the whole rod to the square. But if instead it's moving or is rotating not in the center but in an axis at one end, then it's 1/3. So it is higher than the previous one because we have more mass that is farther away from the axis of rotation. We have other examples as rectangular plate, a thin rectangular plate as well, axis along the edge. That could be, for instance, the door. We have a hollow cylinder, a solid cylinder, a thin-walled hollow cylinders. These cylinders are usually used to, for instance, model pulleys. And we have a solid sphere, 2/5 of mass radius squared, and that could be any given ball or whatever, and a thin-walled hollow sphere, 2/3 of mass radius squared. And of course the thin-walled hollow sphere could be larger than the solid sphere because there are more particles that are away from the axis of rotation. So if we have the slender rod, that's case A, of length L, the moment of inertia is 1/12 of mass length to the square. And there is a theorem which states that, well, if the axis of rotation is parallel, because this guy is rotating at the center of mass, the center of the rod. But if instead this rotates, for instance, here, or it rotates, for instance, here, well, then the moment of inertia will change. And this parallel axis theorem will state that the moment of inertia equals the moment of inertia at the center of mass plus the mass of the rod times the distance to the square, which has changed. So for instance, this distance could be this one, and given this distance, well, we can actually state that this distance is half the length to the square, so we can actually have 1/12 of mass length to the square plus 1/4 mass length to the square. Remember that you square also the half in this situation, and 1/12 plus 1/4 will give me 1/3 of mass times length to the square, which is given in the green one as, for instance, the case which we analyze here, the slender rod through one end. We can also analyze, for instance, other parallel axes with the parallel axis theorem. So this is how we are going to be working with the moment of inertia.